Hello, statisticians. Today's lesson is on types of studies. Let's get started. Fall in the US marks the start of flu season, and in recent years, COVID-19 season also. And while most people recover from these diseases, they can sometimes be fatal, especially among vulnerable populations. In fact, in 2025, over 40,000 people in the US lost their lives to these illnesses. And although that number seems high, the death rates were very different when we first saw COVID-19 in 2020. In 2020, a lot fewer people had the flu due to social distancing measures that took place during COVID-19. But there was a reason for the social distancing measures. COVID-19 was very new, and even with social distancing in place, humanity had not yet built up resistance to the disease. Almost 400,000 Americans died from COVID in 2020. Why was COVID-19 so different from other diseases, like the flu or the common cold? COVID-19 is very contagious. Even beginning with just a few cases around the world, it spread very quickly. And not only did it spread, it was deadly. Many people who caught COVID did not recover. While generally healthy people get sick with the cold or the flu, and they get better with time and medication. For COVID, many people required extreme measures like hospitalization and ventilators, and those often were not enough. Since COVID was so new, humanity had not built up resistance to it. Until we developed that resistance, we needed to find a way to reduce severe illness from the disease. And there was a huge effort to develop new vaccines with a promise to make that happen. These vaccines were developed rapidly. Modern technology and the widespread nature of the disease, which allowed for widespread testing, allowed the vaccines to be created, tested, and approved in less than a year, a timeline that broke records and was seen as a scientific breakthrough. However, this rapid development also led to skepticism, as some questioned whether we could know that a vaccine actually worked in such a short amount of time. So that brings us to today's key question. How do we know if vaccines actually work? With that question in mind, let's move into our notes. We're going to discuss 3 topics today, starting with investigative questions. All investigative questions involve 3 parts. They start with variables. 2 key parts of variables are the response variable and the explanatory variable. Explanatory variables are used to predict, explain, or influence the outcome that we are interested in. That outcome, which we measure, is called the response variable. Also note that the explanatory variable is sometimes called a factor variable. So now let's look at our central question. Did the COVID vaccine actually work? Although this is an interesting question in terms of motivating a statistical investigation, we actually have even more questions. What variables should we measure? What population are we talking about? What statistical analysis should we do? It's actually not a very good investigative question, and that's because it's simply not specific and detailed enough. It doesn't tell us what variables we should measure, what population we're talking about, and it doesn't point us towards a statistical analysis we can do. To guide a statistical study, a good investigative question will have 3 components. It will name the population of interest, it will specify key variables, and it will indicate the expected direction of an effort. It will also specify a comparison group if there is one. To help with formulating investigative questions, we can use these templates, one for questions about causation and the other for questions about association. This is a lot to digest, so let's look at an example. Here's our original question, but now formulated using our template. For US adults, do vaccines cause a reduction in COVID-19 severity compared to a placebo? To clarify, a placebo is an inactive treatment, like injecting saline into a patient's arm instead of a vaccine. We'll talk about placebos in a later lesson in the unit. Let's see how the question guides our analysis. The population is named, it's US adults. Our variables of interest are identified. Vaccines are the explanatory variable, the predictor, and COVID-19 severity is the outcome, the response variable. The direction we are looking is a reduction. We want to see if the severity goes down after taking the vaccine. And in this case, we have a comparison group, and we made sure to mention it. We're comparing taking the vaccine to taking a placebo. Not all studies look the same way or have the same purpose, and we'll break those down into two groups. Studies can be designed to draw conclusions about past or present, and we refer to them to inference studies. They can also be designed to make predictions about the future. We'll begin by talking about inference in this unit, and then we'll continue to talk about it more later in the course. As for predictions, we'll get to that a bit later. To get a bit more specific about inference, those studies can be observational or experimental. The big difference between them is that an observational study only looks at things as they are. Those conducting a study don't interfere with whatever actions or processes are happening. In an experiment, something happens that has the potential to change things. That is, there is a treatment or condition imposed on the participants, which we call experimental units. By spring of 2022, we were past the pandemic. Humanity had developed more resistance to COVID-19 and death rates had dropped substantially. But here, in the first part of the graph, we see the high death rates that happened before we have developed resistance. And if we compared those death rates between those who had received the vaccines and those who had not, we see a big difference. Here, taking the vaccine is our explanatory variable, and the response variable is the death rate, which is lower among those who took the vaccine. So taking the vaccine is associated with a lower death rate. But our question asks, is taking the vaccine, does that have a cause and effect relationship with the lower death rate? Does this graph provide enough information to show that causal relationship? So let's think this through. We start with these two groups listed in the graph. Those that were vaccinated, who had the lower mortality level or the lower death rate, and those who were unvaccinated, who had the higher level of mortality or higher level of death. However, we also have to ask, is it only the vaccine that was different in those two groups? For example, it may be the case that those who accepted the vaccine also tended to be more receptive of other public health guidance. For example, wearing masks more often. They also maybe were more likely to live closer to medical facilities where they could get the vaccine and also could get more treatment if they got severely ill. They might also be generally more health conscious in other ways, like exercising more often. So looking at it again, when we ask what causes the lower death rate, it could be the vaccines, or it could be these other factors that are associated with people who received the vaccine. In this case, it's impossible to tell. These other factors, which present a clear connection, could have confused things a bit, and these are called confounding variables. These variables are associated with both the explanatory variable and the response variable, and they create doubt as to whether there is a true causal relationship between those two variables. In our case, mask wearing, living near a medical facility, and exercising more all confound the potential causal relationship between vaccines and lower death rates. This was an observational study of COVID-19 vaccines. No treatment was involved. It was an observation of death rates without bringing in vaccines. Because we didn't impose any conditions, we can't eliminate those confounding variables. And that means the causal relationship is not possible. We cannot say that we know that the vaccines caused the lower death rates. There are two types of observational studies. A direct observational analysis is when we actually observe and go through health records like we did in this medical study. For this example, we used health records to see who received vaccines. Another type is a survey where we would ask people to self-report findings. Take a minute or two to consider the differences between these processes and the implications of the results. But what we actually wanted to know is if vaccines cause a reduction in the severity of illness. How can we answer this causal question? We have to use an experiment. In an example, we would take all of the participants and we would randomly assign them to two groups. Some get randomly assigned to one group and the remaining get assigned to the other group. Because we are assigning them randomly, any potential confounding variables like mask wearing, being near the hospital, exercising, they would get balanced across the two groups. Now we would impose the treatment. Everyone receives a treatment. Some of them get the real vaccine and some of them get a fake vaccine that is a placebo, like saline, sterile salt water. Then we wait, and then we can compare the severeness of their illness between the two groups. By doing this process, first randomly assigning to balance the confounding factors, and then imposing the treatments, we can now estimate the causal effect of the vaccine. This is called an experiment. An experiment is a study in which conditions or treatments are imposed on experimental units. Experimental units are the subjects, participants are units to which treatments are assigned, and treatments are different categories or levels of the explanatory variable. And when experiments are well designed and have random assignment to treatments, we can see the potential confounding variables are balanced between the groups and that causal conclusions are possible. In the case of the COVID-19 vaccine developed by Moderna, they did an experiment on 30,420 participants, all aged 18 and over. The participants were randomly assigned to receive the vaccine with over 15,000 participants in each group. 14 days after vaccination, researchers measured the illness between the two groups. First, they looked at symptomatic cases, that is, people that felt sick. In the vaccinated group, there were 11 cases, and in the unvaccinated group, there were 185 cases. Then they looked at people with serious illness. In the placebo group, there were 30 people that were very ill, and in the vaccinated group, there were 0 people that were very ill. These results were found to be statistically significant, meaning that the difference between illness and severe illness between these two groups was so large that it was unlikely to be due to chance alone. Moderna wasn't the only maker of a COVID-19 vaccine. The other major vaccines, Pfizer and Johnson & Johnson, also ran large-scale experiments that showed high vaccine efficiency. So, back to our question. We now have an answer. We have convincing evidence that yes, vaccines did in fact cause a reduction in COVID-19 severity. In particular, the effect of a vaccine was what we call statistically significant, so large that it's unlikely to happen by chance alone. We'll return to the idea of statistical significance later in the course. And that brings us to our final topic for today, sampling and being able to generalize our findings. When the disease first spread across the country, COVID-19 tests were provided to people who felt sick. This tells us the proportion of people who have COVID-19. We already know that people are sick. We're learning whether or not they are sick with COVID-19. The problem is that not all people who are infected had symptoms. Some people actually do not feel sick when they have COVID-19, but they can still spread the disease. So by testing only people that feel sick, we are underestimating the true proportion of all people who are infected. So this raises the question, what's a better method we can use to collect this data? One way to collect the data is by census, by measuring all the items or individuals in a population. This would mean testing every person. It's not feasible to give everyone in the whole country a COVID-19 test. It'd be very difficult and very expensive. So in this case, a census is infeasible. And we're already seeing that testing only people that are sick is inaccurate. So what would we do? Well, we come up with a better solution, random sampling. The simplest way to randomly sample is the aptly named Simple Random Sample, or SRS for short. The SRS is a sampling method in which every possible group of n individuals in the population has an equal chance of selection. Now, it's always important to think about how sampling is done because it affects what we call generalizability of results. When individuals are not randomly selected from the population, those results can only be generalized to the individuals similar to those in the study, not the entire population. So, imagining a small town of 5,000 households, if only households where people feel sick are tested, infection rates can only estimate among symptomatic households. When individuals are randomly selected from the target population, the results can be generalized to the whole population. When the simple random sample is obtained from the whole town, infection rates can be generalized to all households in the town. That means that the results can be used to estimate infection rates even among people who do not feel sick. To summarize this, let's take a look at this graph. There are two factors. First, we have whether or not we've randomly sampled. And if we do, we can generalize to the target population. If not, then we cannot generalize to the population, only people similar to those that we sampled. The second is whether we've randomly assigned people to the treatments, not just observed. If we do, we can say there's a causal relationship. If not, we can only say there's an association between any findings. Putting this all together, remember to think about the sampling and the study design when thinking about the kinds of conclusions you can make from a study. And that brings us to our discussion for the day. In the original Moderna vaccine trial, only adults 18 years and older were enrolled. With that in mind, from this trial, can we safely assume that the vaccine would be equally effective at reducing severe COVID-19 illness in children? Why or why not? Take a moment to jot down your initial thoughts to this question and be ready to share in class. That's it for today, statisticians. We'll see you next time.